Right, I'll get, I guess let's get started. It's my pleasure to invite you all to the boot camp of the LLM and Transformers program part 1 this fall. My name is Venkat Guruswamy. I'm a senior scientist and an interim director here at Simons Institute. Most of you probably know about the Simons Institute, but a brief introduction. The Institute was established in 2012 with a very generous grant from the Simons Foundation, who continue to support most of our activities. And every semester, we have thematic semesters on topics of current interest, both in the core theoretical aspects as well as connections of theory to other fields. Typically, we have 2 programs running at the same time, and one of the programs is the LLM thing. And the programs bring together 70 to 80 researchers who are top people in the field, both junior and senior, as well as many outstanding young scholars in the form of our Fellows program. And we had the Meet the Fellows event yesterday, where the Fellows gave talks. And another unique feature of our programs is that it always kicks off with what we call a boot camp, which are sort of tutorial style lectures by experts in the field, which really distill the sort of core things you need to know to kind of get up to speed in the field, because all of us have come with different backgrounds and different skill sets. And these boot camps have really taken a life of their own, not just the week they happen, but everything at Simons is streamed and archived, and these videos are some of our most prized resources for the worldwide community. And this week, it's my pleasure to invite you all to the boot camp of the LLM program, and hope you have a great productive week. And I'll let Umesh introduce the boot camp.
Thanks, Venkat. So let me just say a little bit about this whole program. It's the LLM program is sort of unique at the Simons Institute. It's the first time we've had a program for a full year, and it's sort of clear why we should do the program. Well, one reason is clear, because potentially LLMs are the biggest scientific adventure of our times. But still, you can ask, well, why should we do that? Have the program here at Simons? And so, the basic question we have is, is it really a technological adventure or a scientific adventure? We hope it's the latter as well as the former, right? And the Simons Institute, as Venkat said, is it's really been designed with a view to convening multidisciplinary researchers around a topic, often through this computational lens. And so this seems to be an excellent topic on which to do this, because it's a very hard question to understand why LLMs work, and what they're doing and how we can make them better. So how interdisciplinary? Well, obviously, machine learning is represented here, and it's highly represented here, and also TCS, because after all, Simons is an institute for theoretical computer science. But not just because of that, but because in theory we try to build toy models and try to understand new phenomena in these toy models. Also, through crypto and complexity theory, there's this distillation of definitions of, for example, verification or fairness, and these are really quite important. And also, crypto itself has led to these schemes for watermarking of LLMs. So there's really a connection there. There's also linguistics, where the notion of a grammar and semantics has had to be revised or revisited, and that's really a process that's happening now. In neuroscience, vector models play a very big role, and as well as we hope that this will have insights into computational models for the brain. And finally, also, cognitive science, where there's which has which talks about the essential elements of intelligence, because that's something that we really want to understand in the context of LLMs. And then there's physics, with tensor networks and scaling laws. So there's a large variety of disciplines that have been brought together, and the hope is that through this juxtaposition of all these people in all these fields, we'll get to understand these new phenomena and LLMs and their potential and why they work, at a deeper level. So one of the principles that we've learned at the Simons Institute in convening these interdisciplinary groups is that a very important part of making progress is developing a common language. And what that involves is making sure that we can communicate to each other and take the concepts from our field and distill them down to their essentials, and in trying to convey them to other fields. And of course, it's a good thing to do, to get the community together. But often it's a great thing to do for ourselves, because in the process of explaining and distilling and explaining to somebody else who comes at it from a different viewpoint, we end up learning those about those concepts at a much deeper level ourselves. And so this is one of the aims for this boot camp. The boot camp is not only meant to introduce you to the basic concepts, but hopefully these basic concepts are going to be distilled in a very interesting way. I think the speakers have spent a lot of time trying to do that, as well as to try to set the ground for directions that we are going to be exploring during the semester. Okay, so with that, let me invite Surbhi Goyal to speak. She's one of the organizers of the program, and I would say that the program itself and maybe the boot camp would not have happened without a lot of her efforts.
Thank you so much for that introduction. Thank you. I won't keep you all for long, but welcome to the boot camp and the program. Generally, I just wanted to share some logistics about the program. Just for communication, we have a Slack. If you're not on the Slack, you can reach out to me and I can add you on the Slack. That's the way we're communicating, so that we can start like research discussions, projects, and so on. And there's going to be a bunch of reading groups that have already started, and I think the first sessions are happening this week. After the boot camp. So if you're interested in those are also accessible through the Slack. So I encourage you to attend those as after the boot camp if you're interested. Logistics wise, today the boot camp starts at 10, but tomorrow and day after it starts at 9:30. So just the time, and you can check the schedule online, which has all the information. And we're very excited for a really great set of speakers from all different disciplines, and hopefully you'll find this exciting. We're going to start with Ankur Moitra and Daniel Shu. They're going to give a joint talk where Ankur is going to speak the first part and Daniel's going to speak the second part. Both of them are like people I look up to, and their work has always inspired me, and their papers are almost the first papers I read in grad school. So I'm really excited to hear from them. So I'm going to give the mic to Ankur to introduce how transformers work.
Yeah, I'm good. I got this.
Oh, you already got it.
All right, thanks everyone for coming. So as Venkat told you, a lot of times for the boot camp, the talks are an introduction for non-experts, by a leading expert in the field. I want to caution you that this will not be one of those times. So I do not work in LLMs, but I'm going to try and explain LLMs from my own perspective, and this is designed to be a very interactive talk, so feel free to stop me anytime. And my partner in crime in this is Daniel, who's going to be continuing with the second part after the break. So what I want to do is I want to tell you how transformers work. And actually, I've broken it down into this plan. So I want to start off with some history and background. I want to tell you where language models came from, because it's important to understand the trajectory of these ideas. What were the shortcomings of earlier approaches, and what are the ways that transformers bridge the gap? But I'm also going to intersperse some, history throughout the talk as, my lens for thinking about transformers. Now, I'm going to introduce then the mechanics of how transformers work. What are the nuts and bolts of the most important building blocks of transformers? How do they work in a mathematical sense? But I want to mention that, when I was learning these things myself, I find just the things that are out there alone a little bit unsatisfying because they don't always answer the question of, why. So why exactly are those kinds of mechanics natural when it comes to, creating language models? And I'll give you some of my own personal musings and collections that I've gotten from other people about how to think about transformers from a conceptual standpoint. So that's really what my goal is in this talk. So let's start from the history. So the first language model actually dates back to the work of Claude Shannon around the 1950s. So just to set the stage, historically, this was right on the heels of Shannon's information theory, which laid, as we all know, the foundation for things like communication over a noisy channel, compression. And what he wanted to do was he wanted to understand how these fundamental notions, things like entropy, that govern how much we can compress a source of information, how do they relate to things like natural language? If we think about natural language as a source of information, what is the underlying entropy? So, of course, a naive upper bound is just log of the vocabulary size. But this would come if natural language were really a trivial thing, where there were no syntax and grammar or ideas that were being conveyed. Instead, each of the words was just sampled randomly from the uniform distribution. So what he set out to answer was this question, what's the entropy of natural language? Now, his goal wasn't so much to construct a generator for natural language, but really to understand how much we can hope to compress it. So that was really what his goals were. And he had this wonderful experiment because, he combined both experiments with humans and natural models that, became the seed of how we thought about language models for a while thereafter. So on the one hand, what he did was he gave humans sentence fragments, and then he asked them to fill in the blank. And what was pretty remarkable about these experiments was that humans were a lot better than you would naively think. In a lot of cases, they could narrow the next word down to just a small number of possibilities. This tells us something very strong about the possibility of compressing human language. But on the other hand, he wanted to design some mathematical approaches for modeling natural language and to see how well those did compared to humans as the baseline. So really, one of the things that he did in this work was he introduced a very powerful model that's called an n-gram model. So let's talk about how an n-gram model works, and then we'll talk about what are the weaknesses and limitations of this easier approach to language models. So an n-gram is something where what you do is you look at a window of previous words. So this would be an example of looking at a window of two previous words. I have the words quick and brown, and I use that information about what two words occur in that window in order to predict the probability distribution on what's the next word in the sentence. So if you think about a very trivial example of an n-gram model, what if there's no window? So in this case, what's going on is that your language model is dead trivial because it's just a probability distribution on words. And all you do to construct the sentence is you sample words independently from this base probability distribution. And of course, you would get gibberish, right? Because you wouldn't have things like the verbs coming after nouns, to actually form a sentence. So then the next most sophisticated thing is just to have a Markov chain where maybe the distribution on the next word only depends on what comes immediately preceding it. This is a better approximation, but still not that good. So what you can do instead is you consider a natural limit where you look at larger and larger windows, and each different signature of a window has a different corresponding distribution on what the next word should be. So this is what an n-gram model is. Now I want to emphasize that when Shannon was doing these kinds of experiments, his goal wasn't so much to generate natural language. These still are not good mechanisms for generating natural language. It was compression. But if you think about them as a generative model, then really what happens is that even if you consider reasonable size windows of like 2, 3, 4 words, you're going to end up with, two fairly trivial cases. You'll either end up generating something that looks like gibberish because the whole sentence doesn't parse, even though locally the pieces look like they're okay. Or maybe you'll generate short, uninteresting sentences like, I went to eat, or something very simple like this. But really, there's a data problem underneath it that people had to grapple with from the very beginning. And this, to understand it, it'll give us a bit of breadcrumbs about, the solutions that come afterwards. So if you think about something like an n-gram model where you have a window of size 4, then the trouble is that these n-gram models actually have an astronomical number of parameters. Because if v is my vocabulary size, then all of the different signatures I could get for the window looks like v to the 4. And for each one of these signatures, I have to define a distribution on the entire vocabulary size. So what we're talking about here is that you take v to be the number of words in the dictionary, and you're raising it to the 5th power, which is just an absolutely astronomical number to try and estimate all of these parameters. So even though you know intuitively that past information should still be relevant and you should really think about larger and larger windows, you have the problem that this isn't really a good architecture to access that kind of long-range dependency. So even way back when in what are called the IBM models, people had to grapple with exactly these kinds of issues, and they had a lot of workarounds, which are good things to keep in mind. See, if you think about it, maybe the particular word that occurs in the window is less important than some sort of semantic notion of what it means. So one of the things you could hope to do is maybe you could take words that ought to act as surrogates for each other. Maybe they're interchangeable. So if the third word in your window is big, maybe it doesn't matter that much if I change the word big to large instead. So one of the tricks that they did was they would take the vocabulary size and they would cluster it into different equivalence classes. And this way you could hope to make some kind of dent, but not a really big one, on just how many different parameters you have in your model. But this is really a hint of what's to come, is because maybe it's not the particular word we care about, it's some sort of notion of what the meaning is. And maybe there are different ways to represent the meaning that are more concise. We'll get to those later. Okay, so then, of course, we all know about the deep learning revolution. So, deep learning became the champion very quickly in a wide range of fields, especially in things like image recognition. All of a sudden, milestones that we thought were decades out were, falling left, right, and center. And really, the one thing that we've learned from a lot of the deep learning revolution at a very high level is that, taking models that are nonlinear and stacking them, making them deeper, and also over-parameterizing them so that they have many more parameters than the number of data points you're feeding in, turns out to be extraordinarily powerful in the sense that that's really the secret sauce that, helps you set a lot of records in areas like image processing. So one of the, first approaches that people tried, on the heels of the deep learning revolution was really to think about sequence processing itself as a very deep network. So usually what people study are what are called recurrent neural networks. So you have some building block, which is a feed-forward neural network. But then what happens is that you apply this in a composition over and over again, maybe once per word in the sentence, or maybe once per token. So what happens is that, if you're solving a problem like translation, you might have a sequence of inputs. These are represented by your vectors UT. You pass them into a feed-forward neural network, and it spits out some new state XT. But then that state is fed back into the neural network. And in this way, you're going to take the sequence of input vectors, the UTs, and transform them into a sequence of hidden states, these XTs. And then you're hoping somehow that you can decode these hidden states into another language in order to accomplish something like translating from English to French. Now, these are recurrent neural networks. I'm obviously not going to go into too much detail about them. But, really the main challenges that people encountered with recurrent neural networks, we know that depth helps a lot in terms of the expressive power of the models you're learning. But there's this problem that it's incredibly difficult to train, in a practical sense, these recurrent neural networks because of this iterated composition. So there are a lot of, simple-minded ways to at least get a high-level intuition about what's going on. Because, if I think about things like, multiplying a whole bunch of matrices together. So that's a very simple thing because it's a sequence of linear transformations. And we know a lot of things about the spectral properties of matrices. But, if my spectral radius is larger than 1, and I'm multiplying all these matrices together, what's going to happen very quickly is that I'm going to blow up the norms of things and they're going to explode. If instead I had a spectral radius less than 1, then everything is shrinking incredibly quickly, and they're all going to collapse. So really, one of the difficulties with training things like recurrent neural networks is that you're trying to operate really in the knife's edge. You want to have some model that has information persist for a long time, but the set of parameters that allow that information to persist ends up becoming a target that's a lot harder to hit. So you have to do a lot of architectural changes, in order to actually make this training efficient, and a lot of tools of the trade. Now, I want to keep coming back over and over again to examples from natural language processing. So that's the great thing about, transformers and LLMs, is that we all have intuition about how natural language works. And that gives us some baseline in terms of expectations of what kinds of architectures we expect to be good, what types of properties they have to manifest in order to actually solve the problems that we know that they have to solve. Say, one of the difficulties with natural language is, I introduced these n-gram models, and I told you that there are difficulties when it even comes to n equals 4. But really the truth is that we need n to be quite large in order to get good completions of sentences that are accurate. What if I had a sequence of sentences like this? I grew up in France, where I spent most of my summers. I speak fluent. Can anyone complete it for me? German? No? French? Okay, French. To be fair, my sentence would go something like, I took 9 years of French, and even French people don't think I speak French. So it doesn't work for all of us, but the word here would be French. A human would be very good at completing this, but how are they completing it, right? Clearly, they're looking all the way back into information that's stored not even in this sentence, but in a previous sentence. And that's the reference that they're using to actually fill this in. So this is already a proof of concept that we need long-range dependencies in order to actually complete sentences as well as humans can. So, what ends up happening is that in things like recurrent neural networks and lots of other things that people have tried, it's very easy for the model to have this property that past information, like the fact that I grew up in France, gets overshadowed by the more recent information. But somehow I need that information in order to actually get a good completion of the sentence. So the question is, what kinds of architectures promote these long-range dependencies without having things get washed away, or without having all of these difficulties of training dynamics? Okay, so back in 2017, there was a major breakthrough. It's hard to understate the importance of this paper. It's called Attention is All You Need. It introduced the transformer model as we all know it now. In fact, this paper is so important and widely studied that if you go in DBLP and you look up blank is all you need, you'll find thousands of papers. So it turns out that whatever area you're working in, if you're working on quantum learning theory, probably a good idea is to title one of your papers blank, quantum learning theory is all you need, qubits and entanglement. I'm sure it's a great idea, so go for it. That one's for you, Mesh. So let me introduce transformers. I told you transformers are a fairly complicated architecture, okay? And I want to go through the how they work mathematically. What are the steps that they do? I'm not going to go through everything, but I'll go through the most important parts. And then I want to pontificate on why. And the why will just be, my own musings. I have no promise that they're correct or not. But at a high level, what's going on for a transformer is you can think about it as solving some sequence-to-sequence problem. So maybe what you're trying to do is you're trying to translate from one language, like English, into another language, like French or German. So your input is a sequence of words or tokens. Sometimes you fragment words into a finer granularity called tokens. And you want to go from the sequence of words or tokens to some sort of sequence of vectors that's supposed to represent the meaning of, what these words mean. That's called an encoder for the transformer. And then you need another piece, which is the decoder, that goes from a sequence of input vectors to the actual language, French or German, that you're translating to. So the question is really how these mechanics work layer by layer. What is each individual layer doing, and where do these vector representations come from? And even better, how are they refined as you go up the hierarchy? So just to keep things concrete, in the original paper, people used like 6 layers. So that's, the way you should be thinking about it. And I want to explain the how of how these things work. So, that's where we'll start off with is, what exactly is attention, which is the main driving force behind transformers, and how does it work? And I want to give some shout outs first. So, one paper that I learned a huge amount from, and I just want to put a plug for it, is this very nice paper by Fwang and Hutter, which is called Formal Algorithms for Transformers. So in this paper, they set out in a very natural pedagogical goal, which is what they wanted to do was they wanted to take, all of these architectures that we know are transforming how we think about LLMs, and they wanted to think about, is there a way to fully describe them in pseudocode? So, usually the way that you learn about different architectures, at least if you're a practitioner, is you might read someone's paper and they describe not the full-blown architecture, but just what are the important changes from earlier architectures that you're building off of. So it turns out that if you, like me, are not a practitioner, but you just want to understand how they work at a high level, then you actually have to, go down the rabbit hole quite a bit to unravel what exactly the transformer is and how these pieces fit together. But what's really remarkable about this paper is that, they set out to write it in pseudocode, and they actually managed to do it just in, a very small number of lines of pseudocode. Once I have the basic operations set up, you're thinking about something like 60 lines of pseudocode to have the full-blown description of the architecture and how all the pieces fit together. One more shout out I'm going to give is another very nice reference is this wonderful blog post by Jay Alamar, which is called The Illustrated Transformer, that gives a visual explanation of how the pieces relate to each other. And a lot of my figures I'm going to pull from him because I think he did a fantastic job. Okay, so let's talk about attention at a high level. This is the most important part of the inner workings of a transformer. And maybe you can think about it as the answer to the question, where and how should you look in the sentence for purposes of translation? So let's be concrete. Let's take an actual example of a sentence, right? We can take the sentence right here. The animal didn't cross the street because it was too tired. Now, if I want to translate this to another language, I want to translate it, let's say, to French. Then it turns out that in order to translate the word it, I have to know the gender of it. So each of these nouns, animal or street, has a different gender, which is either masculine or feminine. So I have to resolve what the reference is for. Does it refer to the street or the animal? So in this case, what does it refer to? It's clearly the animal, because the street is not what's too tired, right? But notice the subtlety here, because if instead I took the sentence and I changed the last word to wide, the animal didn't cross the street because it was too wide. All of a sudden, the word tired being changed to wide completely changes the way that I resolve it. All of a sudden, it goes from pointing to the animal to the street, and then my translation has to respect that and change the gender of what the description is in French. So, at a high level, the idea of attention is that we know that the information we need in order to answer certain questions, like what it refers to, is stored somewhere in the sentence. And in translation, we have the full sentence given to us. So in principle, this word it can look at the other words in the sentence and try and use information that they have as a way to refine its own understanding of its meaning, right? And, let me take a brief aside, right? Because, for many people, these things are a bit unfamiliar. So, one of the starting points for a lot of this before I get into attention is really this idea that we can capture some notion of semantic meaning through vectors. So instead of just keeping track of the identity of the word, or like that clustering example I gave you by clustering things into equivalence classes, maybe there's some way to store some information about the semantics of what the word means, what it represents as a vector. And here we're not thinking about this as a vector in what's called a one-hot encoding, where the dimension would be the vocabulary size. We actually want to store it in a much more compressed way, so that the dimension of this vector is much smaller than the vocabulary. You should think couple hundred, couple thousand, something like this, but way, I mean, orders of magnitude smaller. Orders of magnitude smaller. So, it really depends on the application, but you can get very interesting applications of word embeddings just from, words being mapped to 100 or 200 dimensional vectors. Those aren't the state of the art, but, already you can do some pretty cool things. So one of the neat things that you can do with word embeddings, let me tell you a little bit about, one simple way to think about how you can get a word embedding, although there are much fancier and better ways to do it, is you can take something like a huge collection of documents, and maybe you can form some kind of term by document matrix that describes for each document which words and how many times they occur in a given document. It turns out that when you take that matrix and you take some truncated SVD, that gives you a way of representing words as lower dimensional vectors. And it turns out that when you have these kinds of vectors associated to words, you can use them to solve analogies. So man is to woman as king is to queen. French, oh man, out. I said I wanted the talk to be interactive, not like that. All right, queen, yeah? Okay. So it turns out that, one of the ways that you can use these vector embeddings to solve analogies is that if you think about each word as being associated with a vector, which is something that you can extract through a lot of methods through data, through the SVD, through fancier techniques like word2vec, then, hopefully the way that these vectors are organized in space captures some information about the underlying semantics. So here, this is a stylized picture. But if I think about the vector for man and the vector for woman, when I look at the vector difference, if I look at woman minus man, that's the vector that I add to man to transform man into woman. That same vector or something close is what I add to a vector to transform the word boy into girl, or prince into princess, and king into queen. So in this case, when I don't know what the answer is for queen, what I can do is I can take this vector, woman minus man, and I can add it to king, and then I can search over all of my words and their corresponding word embedding for what's the closest vector to that vector difference I've created, and that should be the answer to my analogy. So it turns out that if you do this, you can actually do mediocre on the SATs, not amazing, but there's some pretty fun phenomena. This is maybe my favorite analogy you can solve with word embeddings. Are there any Canadians here? Okay. USA is to burger as Canada is to poutine. That's right. That's poutine. Who knows what poutine is? Okay. Do you like poutine? Oh my God, it's terrible. It's so bad. Oh, can you describe it?
French fries with gravy poured on top and cheese curds.
Oh my God. I need to go for a run just hearing about it. Okay, some people like poutine, some people don't. We can move on. Okay, but now the idea of attention is we're going to work with word embeddings. Maybe I start off with some naive word embedding because, for each word I map it to some vector that's supposed to capture its semantic meaning. But now I want to somehow process these vectors in a way that, has words look at other words and uses, the amount of attention a word gives to another word as a way to refine its semantics. So I can take my word embedding, which I can get through any of several techniques, and I multiply it by a query matrix. This gives me some other vector that's called the query vector, okay? And you do this a couple of times. So you also take the word embedding, you multiply it by the key matrix, and that gives you a key vector. It's very important, and I'll get into this very soon, that the dimensions of the query and key vectors are the same, because I'm going to be taking the inner product between them to decide how much a vector should look at another vector. And the last thing that I have is I have a value matrix. Again, I take my word embedding, I multiply it by the value matrix, and that gives me a value vector. This can be a different dimension, because really what I'm going to do is these are going to tell me how much one word looks at another word. And then I'm going to use this to sort of reconstitute my word embedding in a way and refine it. Yeah.
Sorry, this is a silly question. On the previous slide,
yeah,
when you have like the query matrix, for like if like you have an input sentence,
yeah,
is the query matrix the same for every word embedding in that sentence?
So the query, yeah, so it is, but soon we're going to go to something a bit fancier where there's multiple heads. So maybe hold that thought. Okay. All right. So let's just define mathematically what attention is. It's not so complicated. What's going to happen is that I want to decide on the value vector for some word. And the way that I'm going to do that is I'm going to constitute its value vector as a weighted average of other value vectors. Now, one way to think about this, I mentioned the transformer, it's going layer by layer. And we're refining what the sequence of vectors are. So, if you're looking at the vector, the value vector for some word, maybe it'll mostly look at what its value vector was before in the previous layer, that's fine. But it might also, aggregate information from other words as well. So that's what's going on here, is that he can look at himself, but he can also look at the value vectors of other words in the sequence. And the question is, how exactly do you choose these weights and this weighted average? So you use this expression right here. Let's try and demystify it. So Q is the query vector for my given word. These KTs are the key vectors for all the other words. So as I told you, the inner product between the query vector and the key is what tells you some notion of significance. The larger that inner product is, the more that one word looks at another word. Now I have to turn these things into actually a convex combination. So the way that we do this is what's called the softmax. So I take all of those inner products, they have to be appropriately normalized. This is something that's needed in practice to get these things to behave well. And then I exponentiate them, and then I renormalize so that these alpha t's are non-negative and sum to 1. So this is called the softmax. And if I were to compute these quantities for all pairs of words, how much does each word look at every other word? That's called the attention matrix. And that's a very significant thing when you think about the behavior of transformers. So already we can see some major advantages to this approach, especially compared to simpler architectures that I introduced heuristically. For starters, this notion that in natural language we have to look pretty far back sometimes to get the relevant information. Well, this comes about very naturally. I don't have to worry about how much the information gets damped as I'm multiplying by matrices or passing it through some chain of nonlinearities. Because if the information is just further back, I just hope that the associated inner product with the word that's in the distant past is large. And that's why I get that information, why I store it and it flows. It's just because there's a lot of attention. Right? And the other thing is that the similarity here is computed in a very natural concept space. So remember this notion of word embeddings. We hope somehow that the vectors associated to words capture something like semantic meanings. So we would expect that this inner product, even though it's happening in a dimensional space that's much lower dimensional than the vocabulary size, it's still storing relevant information that corresponds to some kind of natural semantics. Okay, so this is, yeah.
I'm sorry, going back to the slide, I'm puzzled. Because I've used ChatGPT, I have a notion of what a query is. But keys and values, I'm not sure where these are coming from, what they are.
Yeah, okay. I mean, so here, this is, let's stick with this notation. Now, what I'm going to focus on is really the setting for right now, where we're thinking about translation. So here we have the full-blown sentence, and a word can look at every other word. And really, the query is coming from the word in the sense that he's querying to decide which other words to look at. But the terminology can be a bit confusing, but I'm going to introduce this way because this is the standard convention, and this is,
use would be some set of documents that were translated previously? Where do these things come from?
No. So keys, keys are really just, they come from the word embeddings, right? So it's just one word decides how much to look at another word. That word does so by computing his query vector. The other vectors are called the key vectors. And you take the inner product between the query and the key vectors as a way to decide how much word I should look at word J. And we take the softmax. So you shouldn't necessarily, ascribe these things to, things like queries in a database or keys that you're searching for. I think that might just make things more confusing. But this is the standard terminology. Yeah.
Sorry, just to follow up on that awesome question. So are they used symmetrically, the query and key vectors? Like, it seems like you could just swap them and.
No.
Sorry.
Yeah, because here, right? This you can see that as I'm ranging this sum here, it's ranging over t. So my vector, right? That's associated to the word whose value vector I'm trying to decide right now. But that's the fixed query vector, and he's looking at all the other key vectors as a way to decide on attention.
Thank you.
Yeah.
Also on the previous slide, where do these query and key matrices come from? Is this something you train on, or?
You train, exactly. You train on. Now, I think, so I'm not going to focus on training in this talk. That's a whole other beast, and I think Donkey's talk might cover some of this, but you may have to stay tuned for that.
All right.
Okay, great questions. Yeah.
It's a weighted average of all other words, but
Yeah.
you also say you only compute previous words here, and it seems that in order to compute the ith word, you need the I minus 1 values, right? And then you compute the ith value.
So here I'm thinking about it in the context of translation. So what I want to do is I want to take a sentence that you've given me, the full sentence, and then I want to translate it into a sequence of vectors. Now, in this context, I know the full-blown sentence, so everyone can look, in the past and the future. That's fine, right? Now, when it actually comes to doing the translation, some of those issues you mentioned are going to come up.
Oh no, I mean, I just mean in that equation.
Yeah.
How do you have this defines the value for a particular word, and how do you have but it depends on the values of the other words. So
in earlier layers. So this is a process that's happening, as you percolate up. And the important thing is that because it's layer-wise like this, you can actually parallelize a lot of the computation because, each word is deciding what its new vector, its key value vector should be. And then it's happening in layers as you're going up this chain.
So in each layer, it's completely
That's right.
paired over here, and then it
That's right. Exactly. Okay. Yeah.
Word when you're trying to compute the first query vector in the first layer.
Yeah.
How do you get started?
Let's get to that later. But very good question. So that I'm going to add a little bit later because that's a refinement. But let's try and give some intuition for what attention is doing. So I want to do this through a thought experiment. So you see, when we have a word embedding, for a word, just by itself, it's just the modal, embedding for that word. Like if I tell you a word like car, and you're associating it to some vector, maybe it's just the typical vector associated with cars. But as I tell you more and more pieces of information, I reveal more about the sentence, maybe the picture in your head changes. And that's exactly the thing that we want to drive, changing the embedding, of the associated word. So other words in the sentence are going to refine the actual precise meaning that you ascribe to a given word. So let's do this as a thought experiment, right? Imagine I give you a sentence and I'm going to hide most of it. The car was, okay? And so, we have in our mind, let's just draw a picture, and this will be our proxy for what we think the word embedding looks like. So here you can look up on Wikipedia, and you end up with a picture like this. So this is literally the car that's on the Wikipedia page for the word car. This is the world's most typical car. It's a Corolla. It's red. I had a Corolla when I lived in Boston, and I had to parallel park. I know the precise dimensions of this car so that I can park. Okay? It's a perfectly fine car. Red's not my favorite for the color, fine. I'll tell you more about the sentence. So maybe I tell you a bit more. The ... blue car ... was ... right? So now the word blue, whatever the embedding is for this word, should actually refine what the embedding is for the word car, because it's changed the picture in our head. That's what attention is trying to do, at least from a conceptual level. So now, great, we've got a blue Corolla. Better. I've got a blue car. I like it. But, you know, we've moved up in life. We don't live in Boston. We don't have to parallel park a Corolla. Maybe I want an expensive car. All right, so the expensive blue car was. Actually, near us in Palo Alto is a McLaren dealership. So this is a McLaren, right? Very nice, fancy car. You can see each word is refining my meaning. I went very quickly from a Corolla to McLaren. But unfortunately, the last word in my sentence is totaled. Ooh, that last attention was a doozy, right? Totally changed my underlying picture. And, you know, maybe it's changing the word embedding. Because when I think about completing the rest of the sentence, I sold the car for a little bit of money, you know, because it's totaled. All of a sudden, these types of refinements are really needed in order to get interesting completions that have some sort of consistency across the story, because otherwise you're just working with the modal car that's on Wikipedia. So this is some sort of ansatz for how we might think attention is working. Of course, the truth is that attention works because it works and because it's scalable. But, you know, I think a big part of the special program is trying to figure out how we as theorists ought to be thinking about these things. So this is just a thought experiment that might be useful. So let's dig a little deeper. You know, really the state of the art isn't one head of attention with one query matrix. It should be more complicated. So usually the way that you do this is that you take the same strategy I gave you before. You have the word embedding. You multiply it by the query matrix to get the query vector. But now the key is that you do this many times. You actually have different channels. These, in this case, blue, red, and green. But a lot of times you have many more channels than this. So you have a bunch of different query matrices that together, you know, given your word embedding, turn it into a whole bunch of query vectors. And you do the same thing for the key vector and the value vector. And then you're going to do the computation exactly as I told you before. Everything that happens, you know, within the blue part. You're going to take the inner product between the blue key vector and the blue query vector. Use softmax as a way to figure out the attention. You're going to do the same type of thing in the red layer, the same type of thing in the green layer. And then what you have to do before you move on to the next layer is you have to find a way of combining the information across these different channels, right? And so here, one of the simplest things you can do is you can apply some linear transformation that just acts on the concatenation of the value vectors and then maps it down to, you know, what its dimension should be for the next layer. If you didn't do this, then the dimension of the thing would be exploding as you increase up the number of layers. So one of the things, yeah.
Oh, sorry. I didn't say this. How did we decide how to split up the input to the different heads?
So the input goes to all the different heads, and then it does these computations in parallel.
Okay.
And then, you know, the question is really, what does parallelizing this computation buy you in this way? Now, there's some sense in which I could have done all these computations just on, you know, some larger key matrices, some larger query matrices. But, you know, that's you know, what ends up happening is that when you go back through a transformer and look at things like, you know, what are the different heads looking at? Now what I can do is I can choose one of the heads, I can choose one of the channels, and ask for the word it. What is it looking at? And I can look at another channel and change the corresponding attention head and ask, what is the word it looking at? Now, it's a bit hard to interpret some of these things because in reality, they're still fairly dense. You know, it's not like they're very sparse connections. But, you know, what ends up happening is that the different heads seem to look at different parts of the sentence, in particular, maybe because they're different routes for information to flow. So, you know, maybe one way to think about this, going back to, you know, some natural language processing example, is I could take a fragment that looks like this. You know, John and Doug planned to split the bill, but Doug didn't have enough money in his wallet. So he went to the bank before they met up. So who's he in the sentence? Doug, right? Why? Why is it Doug? He's the one who didn't have enough money, right? So now, of course, you know, I have he, and I know it should point to the previous nouns, because those are the likely culprits of who the he is. But in fact, the way to tie break between them depends on some other attributes of John and Doug. things which perhaps could be stored among different, attention heads, because maybe in some sense they act as, different channels for information to flow along. So this is just, a theory of how these things could work. These are things which we're still learning about now, how exactly to interpret what all these attention heads mean, because it's a very complicated thing that you learn. Yeah.
You needed many layers for this information to.
That's right.
One layer.
That's right. That's right. So, we're only talking about one layer right now, but ultimately I have to put together a lot of different layers, and I have to intersperse nonlinearity. Otherwise, I'm not going to be doing something very exciting. But, it's not like these channels are actually literally going to be separated, where you train these things and one is going to be just looking at the nouns, one is looking at the verbs, or something interpretable like this. But there's a whole art to how exactly to read the tea leaves and try to figure out what is the mechanism by which it's doing it. But, one of the questions you could ask is, why don't you just have one head? Why do you have multiple heads? I think, that's a little bit of an open question, but at least when people go back through, they see that the heads are operating in different ways. And it could be that there's some kind of foundation for why that is. Yeah.
Sorry, at initialization, there are no structural differences between the heads other than their initial values, right? They're the same shape.
To my knowledge, yes. Sure, but the slides will be posted anyway, so unless you really want me to smile. Okay. Okay. So, the way to think about it is that really, in a lot of natural language tasks, we need different kinds of information. So maybe these channels are storing different attributes, because you have to know who are the people, and you have to have attributes like which one doesn't have enough money. So, this is at least the natural way, is to have channels that modulate the flow of information to keep track of different things. This is at least one postulate for how these things work. But ultimately, building up towards what actually a transformer is, what you're going to do is you do exactly, what I told you, that you have the sequence of inputs that are these word embeddings. They get processed through the self-attention that creates the sequence of vectors. Now, before you move on to the next part, what you're going to do is you're going to pass them through a feed-forward neural network. That's going to do something nonlinear. We know that feed-forward neural networks can implement very complex functions as a function of these inputs. And that'll give you the next sequence of input vectors that are going to get passed to the layer above it. So you repeat this, a bunch of times, in this case, 6 times. And in fact, there are even other tricks you have to do to get these things to work. You have to intersperse in between these layers some appropriate notion of normalization. So in any case, this is how an encoder works. I just want to briefly mention some of the other considerations. So, one of the things that makes these transformers so amazing is that this architecture is really designed to make the computation highly, highly parallel. Because you're working on potentially a very large input, but you can do a lot of the things that are happening in lockstep, together in parallel. This is much better than something like an RNN, where the processing has to go sequentially. Because I don't know what the next input is until I resolve all the things that happened before. Here, all I need to figure out is, how the information flows by means of this attention, and then a bunch of things can happen in parallel. Yeah?
I think of words and vectors as associated with each other, but in higher layers, are the vectors naturally in one-to-one corresponds to words, or how should I think about it?
Well, usually in correspondence with tokens, but yeah. So, yeah. As someone who, once again, not an expert in these things, yes. But the expert is over there.
You also have residual connections. So
yeah.
Added to the first layer. So between layers, you always add the previous layer.
Feel free to chime in anytime. All right. Okay. So the architecture is designed so that the computation is highly parallelizable. But, at least the way I described it, there's a problem, which is that, the RNNs, they keep track of positional information because I'm literally operating, in composition. But, yeah.
Do you need to enforce them to include multiple routes of information, as you call them?
No. I mean, we just build it into the architecture, and what happens, happens, right? Yeah.
If there are not so many of them, is it possible that they just collapse into one thing?
It could be. So that, we will have to ask experimentalists. Yeah.
If we're concatenating the output of all the attention heads and then doing multiply to collapse the eventually, isn't the difference between one and multiple attention heads like 1 gig attention?
That's right. It is. But it also can change a lot of the aspects of how the network is parameterized. So there's really no guarantee that the training dynamics work in the same way. So there are a bunch of representational questions about whether it's actually, increasing the expressive power, but it's not clear, which of these things are really representational versus, questions about having a more conducive loss landscape for training. So that's why I'm sort of punting on these kinds of issues, but that's a very good question. Okay. All right. So, but we need to keep track of positional information. So, some other tricks that I want to mention that are very important to the mechanics of how transformers work. As Shafi mentioned, there's the question of where do the first vectors come from? So one of the natural things I can do is I can take some off-the-shelf word embeddings or token embeddings. Those will give me some vectors that represent semantic meaning in useful ways. But, that doesn't contain information about which word is where. And which word is where has a huge amount of impact on the meaning of the sentence. So one of the tricks you do is that actually the original sequence of input vectors is not just the word embeddings, but you also add in vectors that hard code some positional information. So one of the simplest ways you can do this is you create some lookup table, where each row represents a different position in the sentence, and then it tells you what the corresponding positional vector is. So if it's the first word, I take its word embedding and I add in whatever this row is in the positional embedding. That gives my input vector. And this way, as you're going up the layers, you can process information that's both about the semantics and about the order, because it's at least covered in this. So there's a lot of work on, getting better position embeddings, and, it's a subtle thing. So, before I pontificate even further, I want to tell you at least, one more important design consideration. So really, transformers are made up of encoders and decoders. What I've been talking about is the encoder, right? Because that's where I'm going from an input sequence of words to a sequence of vectors. And hopefully those vectors represent some kind of semantic meaning so that I can decode them later. That's the job of the decoder, so that I can turn it into French or German or what have you. But now, when I had the encoder, it was fine for a word to look at all the other words in the sentence, even the ones that come later. That's what happened with our McLaurin. But when it comes to decoding, ultimately we want to use this to actually generate the output. So, I can tell you what the probability of the next word is, but if it depends on all the other words, the things that come before and after, it's not really clear how to turn that into a way to complete the whole sentence. So what you really need is you need some mechanism of only looking at the information that comes before to do that. So this is called masking. So ultimately what you do is you have a version of attention where you only look at the sequence of vectors before it. And one elegant way to do this is that when you're computing the inner products, which remember get passed into the softmax, just by fiat, whenever I have a word that's looking at a later word in the sentence that it should not depend on, I'm going to set its inner product to -infinity so that after the softmax, it just gets set to 0 and it doesn't actually depend on what comes later. So, these are the mechanics of how transformers work. I promise some random pontifications and rambling. So, sorry? Huh? I do, okay, all right. So, I've never taken a linguistics class, but let's do this. So, way back when, many decades ago, there's this very powerful notion that was introduced in linguistics by Noam Chomsky called the Chomsky hierarchy. So this was an attempt to try to understand and formalize the syntax of natural language. Now, the Chomsky hierarchy really had profound impacts, especially on other fields, where it led to, notions like context-free grammars that are incredibly important within computer science. But ultimately what this is some hierarchy of increasingly more expressive grammars. So the whole goal was to take natural language and to wrap it in one of these levels in the hierarchy, to say that you can recognize natural language and only natural language in some level of this hierarchy. But the truth is that, this isn't really studied so much anymore because this hasn't panned out the way that one would have hoped in the beginning. Because as you expect, natural language, especially in corner cases, can be quite complex. Does anyone know the sentence, buffalo, 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 buffalo? Yeah? Is that a sentence? Yes. Okay. So I have no idea what that sentence means, but it's a standard example of a corner case in linguistics, right? And no one ever says this in everyday conversation. I'll be a little shocked if in our coffee break I hear that sentence in the middle of a conversation. Could happen. But the way to think about it is that really in natural language, if you want to recognize all of natural language, then maybe it's a very complicated recognition problem. You have a very complicated grammar. But now, maybe the right way to think about, the underlying computations that are done as necessary for natural language is how complicated are those computations in a typical sense, the things you need to solve to actually complete everyday occurrences of natural language. So people way back when, had studied a lot of the Chomsky hierarchy. In fact, there's this very nice linguistics paper by Stuart Schieber, where he gives evidence against the context free of natural languageness. I was really happy because, I've never taken a linguistics class, but I can actually understand this paper because this paper, is really just a math paper. The theorem is that Swiss German is not context free. Does anyone speak Swiss German? No? Okay. So Swiss German, I'm told, is an incredibly complicated language. Certainly if you look in this paper, the types of sentences that he constructs in the grammars are definitely not things you see in every day. But really, it's a proof through some linguistic constructions that the types of sentences that are and are not allowed, they don't satisfy the pumping lemma for context-free grammars. So this is a proof, about the difficulty of recognizing natural language. But as I'm trying to get to, these are often fairly contrived examples. Technically, they satisfy the rules of the language, but they really don't arise in a typical case. One thing that I think is very interesting is to try and understand what kinds of computations you need to solve, in order to complete naturally occurring sentences. I mean, we had that example of, I speak fluent French. That was an example that we could look at and decide that, hey, I do need to look pretty far back in order to accurately complete these sentences. But sometimes the computation isn't just about storing information, propagating it over long ranges. Sometimes it actually involves some genuine computations in a Boolean function kind of sense, right? So, this is a very nice example in a paper by Wang et al. So here what they did is they took a sentence that looks like Mary and John went to a bar. John handed a drink to, can anyone complete it for me? Mary. Why should it be Mary? Unless John's an alcoholic, he's probably not handing it to himself, right? So there's an exclusion principle at play here that, we know that it can't be John, so it probably has to be Mary in this context, right? And so what they did in this very nice paper was that they took, not a state-of-the-art model, but a much smaller model, ChatGPT 2 small, and they used techniques from causality to reverse engineer what are the different pieces of the computation. Someone gives you this giantly complicated computation with tons and tons of parameters, but you have to try and reverse engineer in a simplistic sense what is the computation it's actually accomplishing on these simple sentences. And they used it to find, subsystems within the model, which were implementing a circuit that looks like copy this word Mary, but only as a backup if there's no other word that gets copied into this location. So this is an example of what they called, finding circuits in the wild of trying to reverse engineer what the computation looks like. Yeah.
Seems there's two different things here. I mean, I'm curious, especially with the Swiss German thing. Presumably there that was about the rules of the grammar.
That's right.
Or here I could put Ankur would be perfectly valid.
That's right.
Or John or like.
Perfect. Yeah.
Right?
Yeah.
And the other is the computation that's actually of the meaning kind of level. I mean, are you making a distinction here when you say both? When you say natural, you keep saying natural.
No. Yeah. So that's a very good point. Yeah, all I really mean to say is that thinking mechanistically about language what kinds of computations are being implemented or are necessary to be implemented, you know, it also seems to me productive not just to think about it in terms of a characterization of what defines natural language, but also in a sense of, you know, what typically arises. So that's a very important distinction, but I mean it in a much more blunt way, which is just, you know, everyday language, in order to complete it well, we're solving certain kinds of logical problems as a result.
The Swiss German paper that was about the formal grammar.
That was about the formal grammar. Yeah. Exactly. Formal grammar, so it was essentially, you know, certain modes of construction of the sentence. They find some examples of modes and a homomorphism that, you know, yeah, okay, all right. I read that paper. I wanted to show it off. Okay. All right. So in fact, there are even more complicated examples. This is a really neat one I learned, just to give some of the examples of the subtlety of things that we can all do. And somehow, in order to get completions that compete with humans, these are things that GPT must be doing too. And there's the question of how, right? So I tried to put the trophy in the suitcase, but it was too big. So again, in order to do a translation, I have to figure out what it refers to. So in this case, what does it refer to? It refers to the trophy, because I'm putting the trophy in the suitcase. Notice that if I change the word big to small, all of a sudden it completely changes the meaning of what's going on, because now it refers to the suitcase. So these are the types of everyday computations that we're doing under the hood. And, you know, I guess the main point of my talk, you know, really to introduce the special program is that we all know transformers are amazing, that they enable things that we couldn't possibly have dreamed about, you know, 5-10 years ago. But, you know, I think we need some kinds of ansatz for how to think about them. So let's, you know, go back to the time of deep learning. And certainly one can argue we haven't learned much theoretically about deep learning. I think, you know, that's in broad strokes fairly accurate. But at the very least, for deep learning, we have modes of thinking that, you know, help us. You know, why exactly is this useful? Why is it doing its thing, right? So for things like deep learning, you know, what is the benefit of depth that we're really achieving compared to just an incredibly wide depth to neural network? Well, you know, one of the pieces of intuition that you hear often repeated and is borne out a lot empirically is that lower layers are somehow, for image recognition, are recognizing simpler features, things that are the building blocks of more complicated features. Maybe they're representing things like edges and textures. But then at higher layers, what you're doing is you're creating composite features that are much more complicated. Like, you know, what is this leg of this table? Because I know a table is formed with a top and 4 legs. So at higher layers, you're building complexity out of simpler things. And you can really go back through, you know, neural nets that do state-of-the-art image recognition. And it's very easy to check that in lower layers, they're really recognizing things that look like edges, like a diagonal line. But then you can go back through and try and interpret, you know, what kinds of patterns are making these different nodes inside Fire. You can find these amazing things like, you know, inside the deep network is a cat node that somehow has put together all of these lower level features and organized them into what we call a cat. Or maybe there's a face node somewhere here, right? So these are the kinds of ansatzes that at least we have as a starting point for how to think about what deep learning is, even if we can't prove theorems that, you know, have to do with what's happening in a practical sense. But what about for transformers? You know, I'm certainly no expert in it, but this is, I think, you know, one very important topic for discussion is what are the same modes of thinking about what transformers are accomplishing, right? And I want to caution that I think too general an answer is not useful. You know, let's go back to deep learning again, right? What's an example of what I would call too general an answer? You know, why do deep nets work? Well, the answer they'd give you in the 1980s is just something based on universal approximation. They would tell you, well, it's good because, you know, deep neural networks, even depth 2, they can approximate an arbitrary continuous function arbitrarily well, right? And that's a true statement in a mathematical sense, but it doesn't tell you anything about why we use the architectures we do, because there are tons of other mechanisms that, you know, are universal approximators. I could just create some sort of naive lookup table or something like this. And if I discretize things the right way, I'll accomplish universal approximation. But that would be a terrible way to recognize images, just by memorizing all the examples I've seen before. So somehow too general an answer that really doesn't have to do with the structure of the data, those are the types of things where I think, the theory is very far from practice, and it's not necessarily giving us a meaningful way to think about what's going on. So I'm going to stop there, and we can continue a bit over the coffee discussion. And I want to leave some fun for Daniel after the break. But sure, I'll take a couple minutes for questions, and then let's take a break.
Have questions. One thing you didn't mention is causal attention. Mm-hmm. I'm curious how some of your examples don't jive with that. I'm curious what your thoughts about how that limits or how does this kind of attention mechanism you described happen despite having directional one-sided directional attention.
That's a great question. I'm not sure I have a great answer for that. Can I phone a friend?
So, in transformers used in practice, usually because my understanding is just for engineering considerations, because it makes it much more efficient to calculate the loss on the next word loss on an entire sequence. You only use causal attention, which means that you only have in that formula that Ankur wrote, you only the summation is truncated only to the words before you, not after you. But nevertheless, as Ankur very convincingly demonstrated, we do need the words after us in order to change the meaning of a particular word. And I'm curious, I don't understand, how this happens and why is it that causal attention.
But also, the information from previous words can still be stored at the front of the wave. So it's not necessary that
Is it previous or full?
Yeah, so even that car example, right? Who's to say that it's not necessarily that literally the embedding is describing the word that I'm currently on. It could also be storing information, about words that come from before. So maybe the word, totaled itself has the picture of the car built in. There's not necessarily a one-to-one map between, what the embeddings are, and a lot of the information can still be stored at the crest of the wave, even if it's not literally about that word.
I think maybe just to formulate the question again, if you were translating from a prefix language to postfix language, you might need information from later because total can have the information about the car, but now you need.
Yeah. Did you want to add anything?
I think what Ankur said, main reason is that you want to use this in a generative sense to predict the next token. It makes sense that you're not trying to look ahead, but that's the main you think of this as kind of a natural way to consider which other words to look at. But it's not clear that you couldn't also do this just done more effectively without testing.
But they're actually not always causal, right? The original paper itself has
The encoder,
paper is
not necessarily.
But because they use in a generative sense, right? So what application are you considering?
Even for translation, the way these are used, right, it's not actually because the output sequence can also be different than input sequence, and these are still used kind of even the original use for translation was not literally as taking a sequence and input and having each word in the sequence eventually corresponds to a sequence output. But anyway, I think
Sorry, this is complex.
Yeah.
Any question?
One question is, assuming that we have infinitely large computations, and we are looking at the problem of predicting the next word, and given sufficiently large n, would n ram be the upper bound for transformer?
Are you also assuming enough data to actually do this? The data would just be astronomical for these kinds of things.
Actually, just the joint distribution.
Yeah, I guess eventually it's just the joint distribution. So seems as good as anything.
The data is really important because it's unlikely to see, if you make n really large, it's unlikely to ever see a sequence of every vocabulary combination. So you might never have any data, so you might not predict. So most sequences that people play with generate are slightly different from what exists in data, so don't produce anything in those cases.
So the problem with n-graph is the computations, right?
And the data. The data. The data is actually more of a problem.
Somehow the attention here trying to put weight on the edge so that we can ignore a lot of things and make things very sparse.
It might be that with large and you're over constraining things. So in fact, maybe you don't want n to be too large, like 30%. Not because it's computation hard, but just because it's a bad thing to do.
Okay, I'm going to declare I need a water break, so thanks.